usually within 24 hours. If you have any questions during the webinar, please use the GoToWebinar question tool. You may submit a question at any time during the presentation. We'll reserve time at the end of the webinar to answer as many questions as we can. Today, we are very fortunate to have two industry veterans who are experts in the fields of liquid coating and laminating and corona treating. Lee Osnes is the product manager, coating and drying for Davis Standard. Lee has 22 years experience as a product manager and over a decade managing a coating laboratory. His current responsibilities include configuring equipment layouts to achieve customer goals and provide startup and training assistance for Davis Standard customers. Tom Gilbertson is Enercon's Vice President of Application Engineering and has over 30 years of surface treating application experience. He has authored numerous technical papers and articles on surface treatment and is a frequent presenter at industry events. His expertise and practical approach to the corona treating process make him an asset to customers in both the converting and extrusion industries. In today's webinar, Lee and Tom will cover the key areas which can make or break a liquid coating line success. They'll look at the importance of properly defining the application and understanding how the substrates and product structures influence equipment selection. And we'll also look at the role of corona treating in ensuring coating success. With that, I'll pass it over to Lee, who will begin our presentation.
Good morning. In order to do this presentation, what we wanted to focus on to optimize for your application was to focus on the product structures, which is your applications at the end. And from these product structures, as we dissect through them, we will determine what is the proper machinery equipment to get you to the new lines that you need today. In looking at the structures, we're going to be looking at the coatings, the surface treatments of the substrates, the drying, and the web handling. And then once we get to the coating parts of the structure, we're going to be looking at the coater types, surface treatment again for the coatings, drying of these coatings, and laminators, wet or dry. Next. All right, here's a generic product structure. So for today, what we started with is just a basic label structure. So what we're going to look at are what are the substrates to be coated. And in here, you're seeing a face stock and a release liner. In what order are these webs to be coated? So we'll discuss that different webs can withstand different temperatures, different solutions, solvents, waters. So we want to figure out which is the best order to coat these and bring them through dryers. And based on that, what are the limitations of the different webs? Basically, your temperatures or your tensions. For instance, some of your film substrates, like a BOPP, will soften above 160 F, so we want to be very careful by bringing those through the dryers. Tensions, let's talk about a softened BOPP. We can stretch it, or you put a tissue, we can rip it easily. Boards, obviously, we can pull a lot more tensions. Now, what are the parameters for the web handling? For each web, we need, again, to look at your tensions. What are the roll diameters? What are the roll weights? That'll help us determine your unwinds and rewinds and the tension set points for the entire line. And then what are the surface treatment level requirements? On these, do we corona treat them? Do we flame treat them? Are there no treatments? The actual treatment levels and stuff will be discussed by Tom later. And then what are your formulations? So we'll look at the different coating solutions that are applied. In this structure here, you're seeing an adhesive layer and a silicone layer, and we'll tear those apart. And then how do they get applied to the web? Those are the different types of coaters that we would select and which one's the best for that particular application. And then we'll talk about how do you dry these formulations. So we have to understand the basics of the coatings and the substrates, and when they're combined, what would take to get them through a drying process or a curing process. And at the end, what are the safety and design parameters of the formulations? Okay. Here is the same product structure I showed you, and here's how we break it down and figure out how we're going to bring it through the machine line. So in the first, we're going to use the release liner, which in this case we're going to say is a film substrate. Okay. This we're going to call as a liner, and it will be the part that we'll be coating with the silicones. So on the main unwind, we're putting the film, going to coating station number 1, we're going to apply a silicone, and then we're going to go through a dryer and dry or cure, depending on what stage of this formulation we're in, and create a silicon-coated substrate. We'll make this a 2-pass line, so now we're going to take that substrate coated off the winder, we're going to put it back on the primary unwind again, and now we're going to apply a laminating adhesive to the top of the silicone. And in this case, we're going to laminate it to a paper web, which is your face stack. And the reason we're doing it in this order is the face stack is usually the expensive web that is used for the labels and that you're going to be displaying, and you want to put that through as little stress as possible. And going through dryers and tensions and laminations could stress these substrates. So on that second pass, once we laminate it to this paper, you'll see on the primary winder, we created that generic product structures with the substrate being a release liner, the silicone coatings, then your laminating adhesives, and then your actual face stock, which in this case was a paper laminate web. Okay. Now, we'll start with coater selections. So with the silicones or with those adhesives, what we need to look at is the basic parameters around the requirements of each of these coatings. So at what line speed are you going to run these? All right. Speed will determine tensions, style of coaters, length of dryers, amount of temperature and dwell time in a dryer. All right. Then we're going to look at what substrates. All right. What's the best coating application for a substrate? If it was the film or the paper, you know, a gravure coater, a slat die coater, or a multiple transfer coater works great. However, if we had chosen a fabric or a tissue, then you really don't want coaters that create back pressures because it could penetrate through the web itself. So we need to isolate what your substrates are for each product. Then we'll look at your coating formulations. Within the formulations, we're going to break that apart and go through the different parameters like the solids, the viscosities, which a slider tool will go through. And then what's the finish criteria? At the end, what is it you're looking for? Is this going to be an optically clear product like a window film? Or is this going to be a tape and label that's a paper that you don't see through? Or let's say a label that has a film that has print on the back side. So we need to know what your finish criteria is to pick out the right equipment. And then what's the end use? What is your product? What are you going to do with this? Is it going to be outdoors, exposed to the weathers? Is it going to be an indoor product? Is it going to be on heated substrates? Are they going to be, what are we going to use them for? Okay. And then we get the appearance. Obviously, that covered a minute ago with your window film. I need optically clear so I can see right through it. But let's say I'm making playing cards, all right? I'm laminating two structures together with a black adhesive in between them so that you can't see through the cards. That appearance is not as necessary. And then what's the company's geographic location? What we're looking at there is what are your outside temperatures? What are your humidities? What are your altitudes to design our drives? The dryers are basically, you know, am I going to pull air from inside or am I going to pull it from the outside world? Like here in New York, during the summer, it can be very hot and humid, where in the wintertime, it's dry, but extremely cold. So that sizes our dryers, and we look at the burner sizing. And then state regulations. What type of equipment can we put in? What type of coatings can you run? Do we need to add, let's say, an oxidizer to handle all air that's taken off, like the liquids that are removed from the coatings? If they're solvents, are usually destroyed through an oxidizer. Ozone can sometimes go into the atmosphere. Other times it goes through the oxidizer with the rest. And then quality of the workforce. You know, this is a sensitive one, I understand, but if we're in an area where you're changing employees, they're constantly moving from one job to the next, we would look at doing a coater that's easy to train, like a gravure coater versus a slot die, which would take a couple of weeks for you to really understand. And you want to maintain those people year round. So we use all those basics to select what coaters we're actually going to put in. Now your basic coater types, and all I'm going to do is the most used, the most common ones here. The gravure coaters and any variation, whether it's a kiss, a reverse gravure, a forward gravure, offset gravures. Reverse rolls, where you have two precision chrome rolls running very close, creating a gap between the two. Both the gravure and the reverse roll could be used for the adhesives or the silicone on the gravure. Slot die, you know, if I'm doing the adhesive coating and we're going to run the same adhesive all day, a slot die is a great coater to put on there. However, reverse roll and a gravure and a rod would also work with those adhesives. Rod coaters are very low-cost coaters, which you put on an excessive amount of coating, like you put on more PSA than what you want your adhesive, and you meter it off with a wire wound rod or an engraved rod in today's standards. Smooth roll coating, that could be considered for primer coatings, for your silicones, for, you don't really use it in the adhesive market, but for other coatings out there. An air knife coater, again, that's an excess coater where you're going to put on more coating than what's needed, but then meter it off with an air knife, which will blow the coating off in a uniform fashion. This air knife and the curtain coater I'm going to talk about next actually gives you a very uniform coating layer on a substrate. So if I got valleys, if it's not a flat substrate, peaks and valleys, at the peak and in the bottom of the valley, I'll have the same coating thickness, where these other coaters I just mentioned will give you a flat coating. So it'll fill in the valleys. It won't be as thick on top of the peaks. Curtain coaters are fairly newer in the industry. You need to be formulated to run these. You can't take existing coatings in most cases and apply them. But what this will do is apply, let's say, for these label products, your adhesives. And it's about 6 inches above the web. It'll drop your adhesive onto a moving web at speeds above 400 feet a minute up to 3,000 feet a minute. The advantage is I'm not touching the substrate. I'm not abrading it. We don't get any streakings or buildups. And it also gives you the same thickness of coating in the peaks and in the valleys. Dip and squeeze, that's where we're going to dip the web into a tank of coating and then squeeze it between two rolls. On tape lines like masking tape, this is how you would treat the crepe paper, and you would saturate it with a coating that would give you the elasticity and a release factor for your adhesives. Knife over roll is another method that was usually older technology. This is where you put a precision knife edge right above the substrate, and the gap of that knife to the substrate creates your coat weight, but you fill a pond and then this just scrapes it off. It doesn't give you any good appearances, whereas the reverse roll, by changing speeds of the applicator roll and the metering roll independently, we can create a mirror effect. Hot melt coatings, those are adhesives. They're used in tapes. They're used in the labels. They can be applied through gravures, slot dies, reverse rolls. There are multiple methods to do these, and depending on what your products are, what your hot melt requirements would be would determine those. Yeah, and as you can see to the side there are countless variations of each of these. Typically, you're going to use maybe 10 different coaters, and with all the variations, you're looking at over 50 different types of selections. Okay, next. On the coating formulation properties, all right, I mentioned to you a minute ago the silicones and the adhesives. What we look at there is what are their functionalities. We want to identify these. Silicones are typically a release coating. Adhesives, they're typically going to be a tacky, or it's going to stick to a web or hold a label to your products. We want to know what the end functionalities are to identify them. And then what is the coat weight? How much coating are we applying to the substrate? Now, this is usually going to be either a wet or a dry number, and either or we need to know them both so that we know at the end on the winder what we're winding up. But during the drying process and the application, what's that thickness going to be? You know, and what are we putting on? We figure this wet film thickness out based on the solids content of that coating and the actual amount of coating you're asking for. And then density will actually play a part of that. Most of your adhesives are slightly above a 1. Water is a 1 density. Adhesives are like a 1.1, slightly heavier. Whereas there are some solvents that, if I'm using a solvent-based adhesive, some of your solvents are much less in weight. When I say a 1 for a density, that's 8 pounds to a gallon, 8.3, where like adhesives are about 9.5 pounds. Some of your solvents can be as low as 6 to 7 or 8 pounds to the gallon. So density has a fact in that. It tells us what these wet film thicknesses are. And a wet film thickness is used to determine gaps, such as on a reverse roll coater, what are the gap between the two rollers? On a rod coater, what's the size of the wire that we're going to apply? On gravure coatings, what's the actual cell formations of the gravures that we need to apply it to? And, you know, again, through the thicknesses, we figure out how much of this we have to evaporate out. In solids, that's the actual part of the coating that once you're dry and you wind it up, that's the part that's left on the sheet. Most of the time we say we're 100% dry, but there are some coatings that retain a little bit of moisture in them. Your substrates will typically, if they're a paper, be about a 6% moisture, but your coating will be less than 1% left in it, depending on what your products are. Medical tapes, medical bandages, the adhesives can't have any of the solvents left in them, so we have very long dryers in order to get the retaining point percentages out of those products. Viscosities. Viscosity is a measurement of the flow of the liquid. So in this case, if you're running a viscosity like water, which would be about a 1 centipoise, a reverse roll coater would have a pond on it or a fountain feed or a pan feed. If it's water, I can't use a pond because it'll fall right through the gap. A higher viscosity, something like a syrup or a motor oil type viscosity, something a few hundred to 1,000 centipoise, you would run with a pond fed between a gap. It also determines the angles of the webs once we leave the coater going to a drying medium, like an Air Force air dryer or something. If it's a water and it's too thick, it can actually create a waterfall effect drilling back down off the web. Now, shear stability. Each coater actually creates a little bit of shear when you're applying the coatings. If your coating is not a stable coating and breaks down, then we want to use a very low shear application method. Whereas if it takes a shear to apply it, then we might add more rolls. Like on silicone coating, 100% solid silicone coating can be done with a 3-roll offset gravure coater, which is typical for the US markets, or a multiple roll, such as a 5-roll smooth transfer roll coater, which is typical for European markets. Each roll is nipped together. It'll be like a chrome, rubber, chrome. And each roll runs at a different speed. So this nip impression in between the two and the difference in speeds create a shearing action. And what this does is it lowers the amount of coating at each nip as you go up, and also will make it flow out onto your sheets. It's actually shear thinning the coatings and gives it a better wettability on the substrates we're going to be applying it to. And then we want to know what's the percentage of each component. This is more toward our drying components. We got to know, is it all water? Is it a solvent with multiple different solvent levels in? What percentage of each? So we can look at evaporation rates, how much energy is going to be required. So we'd like to break that up and know exactly what we're drying. And then percent coverage. In most cases, you're going to coat the entire web, right? And typically we leave a dry edge, especially with an adhesive coater. So a silicone will coat all the way to the end, whereas the adhesive will leave a little edge on the end that uncoated, maybe 1/8 to 1/4 inch. This is so that the adhesive doesn't bleed out when you're winding it. But when I say complete coverage, that's what I'm referring to. There are occasions where we're going to do a pattern coat. So on some labels with adhesives, you're only coating a certain area that will be applied to the next unit so it'll apply. This could be a tape for an automotive or a type of a tool or something. So we define the amount of coverage in percentages so we could figure out your overall coat weight has to be broken up into the thickness based on the percent coverages. The next one we always ask is the pH. This determines more of the materials that are going to be used in the constructions and web handling throughout this machine life. Very high pH coatings require a stainless steel. Very low are acid-based, and we need proper types of materials to cover those. So in some coatings, you cannot use brass. They will react with the coatings, whereas in other coatings are very neutral, and we can just put standard anodized aluminums or painted steels on them. Right. Then is your coating formulation solvent-based or a water-based formulation. Solvent-based requires that we handle the exhaust, leaving the dryers. Normally, it's either going to be in a recuperative mode where we're going to try to put it through a carbon bed and get your solvents back out and reuse them, or it's going to go into a oxidizer, which heats up to very high temperatures and destroys the solvent so it doesn't go into your atmosphere. Solvent-based also requires a design on the machinery to be made so it's explosion-proof, flame-proof. So we'd either put enclosures around those areas that are wet, or we would design special electronics where it's air purged or sealed off. Water-based, again, if we're going to use water-based, it's much easier to handle, but sometimes harder to dry. Dryers might be longer. Evaporation rates on solvents versus waters are different, so we need to identify these. Also, if you're running both on the same machine, in a dryer process, we use LFL detectors, which is lower flammable limits. And if you're only doing solvents, you could buy a certain brand. However, if you're going to put water through the same dryer, you need to buy a more advanced version of that, which is a little more expensive. If you don't do this, then you could actually damage your LFL sensors. And then application speed. Right? What speed are you looking to make these products at? Each coater will require a different limitation per formulation and speed range that coaters are designed to handle. Also, your dryer lengths will be determined based on speeds. So the faster you run, the longer the dryers are going to be, the more cost you're going to put in front, the more building space we're going to require. And then the last one is your application temperatures. All right, we need to know if we're going to be heating these coatings, if the rolls in the coaters need to be heated, your coating supply systems, whether or not they're heated or cooled. And in a lot of cases, the coater will be temperature controlled. It won't really be heated. We're going to put around an 80-degree Fahrenheit water through it because the shear that's created within your application method will actually make rolls swell. They're made out of steel. They will swell, become larger. And we want these to maintain constant all day long. So if you put a known temperature through and control the roll to a set temperature, your process is constant all day long. However, some coatings do need to be heated. You'll find, let's go back to the silicones, 100% solid thermal silicone will carry usually less than 1,000 centipoise in viscosities. But when you start putting additives for controlled release agents, or you get into the UVs where you're putting in some initiators, those viscosities tend to climb. And on a smooth roll coater like the 5-roll, the higher the viscosity, the higher the coat weight generally tends to be. We need more shearing actions. By increasing temperatures on those particular coatings, heating the rolls up, heating the bath up, we could actually lower the viscosities and get you a lower coat weight. So that's where we're at with your application temperatures. Okay. What we're showing you here is two different styles coaters. Basically, the one that's on the left is what we refer to as a dedicated coater. The one on the right will be a cartridge coater. And what we ask here is how many formulations are you going to run? How many products? What is your view for the future? Are you going to run this product forever with one product? A dedicated coater works for you. You put it in, you run that coater day in and day out. However, if you're going to run multiple products on the same line, that requires different types of coater applications. You would be looking to do, let's say, the cartridge style coaters that you see on the right-hand side. With these, also, if the coat weight changes, we can change. This is a gravure coater you're looking at here. We can change the pattern of the gravure roll so that we can change coat weights very quickly with a cartridge. You can have a second cart to the side that we just slide in, 15 minutes, you're running again. Whereas if this was a dedicated, we'd have to roll that gravure roll out with a maintenance crew, and you're down probably 45 minutes to an hour. The coater that's on the left, that's actually a 5-roll transfer roll coater, applying silicones for release liners for the tape products we were talking about. These are dedicated, and you're going to run these day in and day out. They can be altered, but it would be a mechanical alteration, which means you're going to be down 8 hours or 1-2 shifts changing things out on these. So really, we need to know what your plans are for products to determine what style coaters are required, whether we go dedicated, which are lower cost, or cartridge, which could be slightly more expensive, but in the long run, cheaper to run because less downtime. Okay, next. So now we got the coating formulations figured out. Now we need to know what we're going to apply them to, okay? And if you look at this list of substrates I put on here, we have papers, films, tissues, metals, foams, nonwovens. All these substrates can be used throughout all kinds of products, but each one of them has its own characteristic that we need to look at, identify. We need to look at the absorbency, all right? Paper. If it's a clay coated, it has little absorbency. If it's release coated with silicones, it has little absorbency. But if it's an open face craft or an open board, your absorbency actually increases, which that means is as I apply a liquid coating to the surface, some of that liquid will migrate down into that substrate. That requires more energy in order to get that out during the drying process. It also determines what type of coater. If it's a very absorbent, like the tissue is, we don't put a backup roll or a die against a roll with pressures. Something like this, we need a very low backing pressure, like a tissue would be a kiss coat. So we would put 2 idlers. The tissue would go over a gravure roll with nothing pressing it down other than the idlers on both sides, or maybe a die in between those 2 idlers, applying the liquids to it, all right? Whereas film holds out great. It's got very low absorbency. Most films have 0 absorbency, but yes, there are some hydrophilic films out there that do, in fact, take absorbency, and we need to know which ones those are, because again, that affects our drying processes. All right, then you have like surface tensions. Surface tensions are where the intercon group here is coming in, where Tom and Mark are going to be talking to you. Depending on what that energy is of my coating that's being applied to the substrate, you may have to change the surface tension, the energy of that substrate, and you do that with a corona treater or flame treaters, which again, Tom and Mark will explain in a short time here. Solvent-based coatings wet out much easier than water-based coatings. So again, we look at all these different substrates based on these numbers for surface tensions. Strength. All right, a metal is extremely strong. If you're going to get a wrap up or have any issues, you want to make sure you design your idler rolls so you don't break them, bend them, pull them out of the machines type things. Whereas tissue breaks extremely easy. So depending on what tissue product you're making today, the weight of the liquid in the tissue could, in fact, tear the tissue if that stretches too long. So in this case, you'd probably apply a coating right at the coater and then go straight into your dryer as short as possible. You also do this with like a crepe paper making masking tape. The dryer's right next to the coater. However, some of these others, we'll put the dryers upstairs to save floor space. So all these other products are strong enough that when they're wet, they can go the distance from the bottom floor to the second floor where your dryers are. That's what I'm referring to on the strength. Also on films, as the softening temp increases, films get very weak on some, like a polyester, you can go 400 degrees and typically you don't have any issues. BOPP I mentioned earlier, about 160 F is softened. You can start stretching it and tearing it. PE, polyethylenes are like 100 degrees, 120 degrees. So we're going to look at the strength of these inversing to the softening temp of them also. Smoothness. All right. Some products require a very smooth finish, whereas I'm going to run a paper on here and we want to put the adhesive on, but adhesive is a little more expensive, so we don't want to put as much on. You might put a third coating on here. Instead of your release liner first, putting your silicone on, maybe you put in a filler with a scrape coater, so we fill in all the valleys, maybe with a clay style coating. Make it very smooth and then put your release liner on it so that your adhesive is much less required to fill in those voids and make it stick. Also, what is the smoothness of the substrate when we're done with the product? That determines what type of coaters we're going to be applying it with. Caliper, that's the thickness of the webs, right? The thickness of the web has a lot to do with setting up the coater as far as gaps controls, but it also on your idler rolls to transport a web. If you're going to run, let's say, a triple up foil, we got to handle that at the speeds without creasing it. A paper can run a smaller diameter idler because we can pull a lot of tension across those idlers, whereas a triple up foil needs a little air boundary to flip. So we use a larger diameter to create a hydraulic force of air underneath it. Whereas board, heavy duty cup stock boards and stuff, you need larger diameters because of creasing and bending and cracking of the board. So you've got to have small, large radius turns. You can't use the small diameter idlers. So we're looking at calipers for multiple reasons of the substrates. Softening tent, I just mentioned quite a bit already about that, and heating up different substrates and softening them to the point where they can be stretched. Bend radius, again, goes back to your heavy board versus some of your other substrates. Maybe a heavier metal, we would use a larger diameter to get a bend radius so we don't crease the metals also. Okay. Next. Here's one I like to put up. I know Tom's going to talk about this quite a bit, but what I look at on the coaters is these are the basic films in their virgin modes, and what are the surface energies before they're treated. And then I'm looking at either printing, coating, or laminating. What is the actual level of treatment that we need to apply these different coatings, whether they be water-based or solvent-based coatings? So you can see here with the different substrates, when I mentioned earlier, we're looking at surface energies. What am I applying? Now I can see I do need to treat these webs before I could actually apply a liquid coating to them, and how much I got to apply, which I'll let Tom and them guys go through all that with you. Okay. Next, drying. All right, now that we've got a coater selected, we know how to apply this. We know at what speeds we're going to go. We need to start picking out some dryers. So in dryer selections, when we look at it, what we need to consider is what the substrates are, which I've covered in detail already. Is the substrate going to soften? Is it going to be strong enough that we can pull the tensions? Would I use a flotation dryer, or will I use a roll support dryer? What the differences would be, let's say on a film that's going to soften, it's going to become very frail. We want to support it. We'll use like a roll support dryer for that. Whereas a paper, I can use a flotation, which now allows me to put heat from both sides more efficiently and more aggressively, so I'd use a shorter dryer. Coating formulations, again, I mentioned to you that we want to know what that formulation is, so we can look at how much heat to be applied to the evaporation rate to dry that product, to turn it from a liquid to a gaseous form without disrupting the top layers or other layers. If you dry it too fast, you can actually get a skin formed on the top, and now the liquids underneath can't get out, so they'll start to boil and blister and break through the surface. Something like that, you want to dry more from the bottom on the thicker coating to start with than you do on the top, and maybe even a quiet zone where there is no drying on the top, right? Evaporation rate, how much energy is required to turn that liquid from a liquid to a gas, and how fast can we do it without disrupting the surface or the actual coating layers. Solvent or water-based, again, the dryer design to handle solvents, to take them outside and destruct them efficiently without them escaping into the rooms. Water, how much water can each zone handle as far as recirculation goes? How much can I bring back in? On a recirculation, what you're going to do is you're heating up air, applying it to the substrate, and creating a gaseous form, which then goes out through your exhaust. To cut your costs down, you don't want to have to heat virgin air all the time, so you can recirc some of that heated air back in. The more water you have in that air, the less efficient your drying is going to be. So zone 1, maybe a low evaporation or a low recirculation number would be used, whereas in zones 2 and 3, I can increase the amount that I'm recirculating, cut down my operating cost. Solvents, we need to keep those below a standard level, referred to as LEL or LFL, lower flammable limits or lower explosion limits, to keep it safe. And there we'll balance our recirculations, our temperatures, our evaporation rates to maintain levels that are safe in the LFL world. Temperature limitations, again, that's mostly going to be your substrates, but there are times where we're going to have coatings that need to have temperatures, whereas the next one here where we talk about cure and dwell requirements, they require a very high temperature for a period of time. So there are limitations. Sometimes I need higher temperatures, other times I need lowers. Nozzle designs. Nozzle will be what type of air are we going to impart onto the web. You can have a direct impingement where we're blowing hard against the web, or you can have a laminar air which blows along the web. Stainless steel, release coated, they're all different types of nozzles, and for different products, different constructions, we use different ones. Quiet zone, I just mentioned that to you. That's where we have no air on the top, but we're applying a little heat. That allows us to keep a low LEL in the dryer, but yet allows some evaporations to occur so we can start our drying process. The cooling zone, that's at the end of the dryer. In many webs, you can actually just exit the dryer and go around some rolls that are chilled. But when you're talking adhesives, many adhesives, it's easier to add another zone of dryer and blow chilled air onto it and cool it, because to take that particular product around the roll, the adhesive could actually peel off, transfer from the web to the chill rolls. So a cooling zone in those applications would be much better suited. The two charts there are the next two slides, so we'll move on to those and I'll explain those two charts to you. In silicone, what you're looking at for a dryer is you need to heat the silicone up and then to a temperature, and you need to maintain that temperature for a period of time. So that's your dwell length. Now, those numbers will be given to you by your silicone vendors for each product. So if it's a water-based or solvent-based, stage one is not only heat up, but it's the evaporation. We get rid of that. But most solvents or silicones today, they're going to be 100% solids in this talk. So we heat it up, let's say 230 degrees Fahrenheit, and we keep it at that for a dwell time. What the dwell time versus dryer length versus line speed, there's a nice chart here to show you. Let's say I want to run 1,500 feet per minute. You see that 1, 2, 3, 4, 5 down on the blue. And I want to run it for, let's say, 2 seconds at that temperature. So stage 2 dryer will need to be 50 feet long. And there's a formula that you can calculate your dwell times and your dryer lengths to the side there. Okay. Next slide now is for an adhesive coater or other types of coatings, but in this application we're talking adhesives. Here I don't need to cure it. I need to get rid of the liquids. I need to dry it down to a very finite dryness at the end, where it's usually less than 1% moisture left in there. But in here, the stage 1 is where we're heating the web up and heating the coating up to get to the point of evaporation. Now, as a liquid evaporates, it actually creates a cooling effect. So in stage 1, we can put enough temperature to create all this and run it actually higher than we can in stage 2, because stage 2 is where you're actually drying with very little moisture left in there, so I don't have the same evaporative cooling. So now I got to run maybe a little lower in my temperatures for that zone. Okay, so stage 2 is where I have very little evaporative cooling, but yeah, I still have moisture to get rid of. And then stage 3 is where I do my final drying. So if I'm going to get, let's say, from 5% down to 1%, at this point I have no evaporative cooling, but I got to get those moistures out, and I can't boil the coating that's there. It'll blister in a different form, whereas in stage 1 it creates a skin when it boils it first. Over here I'm boiling this almost a solid, which creates craters. So stage 3 is where I'm trying to get the final out at a different temperature level. So these are the 2 different styles of drying that are required for different coatings that help us determine dryer lengths, dryer parameters such as nozzles or designs, other units such as that. Okay, so now talking about all those parameters, now you're ready to figure out what kind of a line that you need to make the products that you want to run today. So I just put on a typical coating laminating line. This one can be used to run a silicone web and then on a second pass laminate it. So if you look at the drawing on the top, the column to the left tells you what the add equipment is. So we need to determine an unwind in there. In this case, it's going to be a dual direction turret with an automatic splicer. So this will be a continuous operation. We won't stop. We'll splice at speed on the run. Other applications, maybe you put in a single position, you stop every time you change a roll. The next piece is going to be a treater pull roll. This is the control tensions going through the line, pulling it off the web, establishing your line speeds, and treating the web if my web needs to be treated for the liquid coatings I'm applying to it. Then we select the coater to be put in. In this case, I'm showing you a cartridge style coater. We call it a Series 4000. And we'll apply your liquids at this point, and I still have to maintain a good temperature or tensions through here. So I put a suction roll above it. That helps pull the web through the coater, even though now I'm changing my weight of that web, so my tension changes. So I have to have a new piece upstairs, which we use a vacuum roll here, a suction roll, to create that. It also controls the tension through this dryer. We're showing you here a flotation dryer, flat, 4 zones, okay? When you exit a dryer, you have camber in most webs, which means if you roll this web out on the floor, you'll see like a banana shape to it. So as you relax it with the lower tension in the dryer, some of this camber can actually affect the alignment of the web in the dryer. So as you exit, you use a guide. And here we're showing you a 90-degree edge guide. So we get the web back to the center so we know exactly where it is, and we bring it down to the laminator section, which now to the right end, we show you another turret unwind. Here we have a 2-side treater pull roll. So I treat one side for improved laminations. I can treat the opposite side for printing or whatever my next step's going to be into that laminator. And we will take the web guide upstairs that senses the web and match it to the web that's coming in off this unwind. It's called hunt and chase, so that they're laminated straight to one another. Then we go through a final cooling section where we bring the room down less than 100 degrees to the ambient room temperature so that as you wind it, the roll stays stable through the rest of your process. You also will have on here a mainline controller, which we call an integrator supervisory. That runs the whole line. You have AC vector drives that are sized appropriately to handle the different webs and speeds that are going to be going through here. And your optional equipment. Right, solvent, we put on solvent coating designs, which the dryer now needs to be LFL monitored, needs to have an oxidizer, put an enclosure around the coater. Optional equipment are different types of coater cartridges, different dryer designs, sometimes customs, where we put a quiet zone in the front, or we use different style nozzles. Maybe we do the roll supports. Coming out of there, the last dryer, you can add a cooling zone if it's an adhesive coated web. You can add a Steamex. What a Steamex is a unit that applies moisture back to a web. So when you're drying, let's say, a silicone-coated piece of paper at an elevated temperature, the paper goes in the oven generally at 6% moisture. When it comes out, it's going to be reduced. And you want around 6% to be stable. What's sitting on the table in front of you is usually around a 6% on your notepads. So you apply the moisture back in. You can do it with a roll method. You can do it with a shower spray. Steam is the most efficient way because steam particles can penetrate silicone coatings, whereas waters cannot. And then you can also look at post-roll coating, such as another dryer pass or a suction roll at the end of the dryer to help you control the tensions. Longer dryers, in a dryer, you want a lower tension you want on the rest of the machine. So if you put suction rolls front and back, you can actually lower the tensions in that dryer zone and control it better. And coat weight gauges. How much are we applying so we know automatically instead of doing samples at the end of each roll. Okay. Then the next slide is, now that we've told you all this information, you say what coatings work with which coaters, or if I have a coater, what coatings can I apply with it? This chart is something that we applied. It's a coater application selection guide. The top row is different style coaters, and these are the most predominant coaters used in the industry. The couple rows underneath them tell you what the suggested maximum speed of those coater ranges are, what the solids are for each of the coaters, solids ranges, viscosity ranges, because I told you earlier you can't run the same viscosity on all coaters. and the coat weights that those type of coaters can apply. Now, this is like an 80-20 rule. 80% of the time that's true. There's always an exception to the rule, so that's your other 20. Now, if you go to the left side and the columns you have, we put some coatings on there that are in family groups like adhesives, inks, silicones, specialties. And we describe what those applications are, what those coatings really are. 2 components: water-based, solid pigment coatings, adhesives, silicones. So that if you have a coating today that falls in one of those families, you can identify it here. Now, with those particular coatings, they fall in the families also. What are the solid ranges and coat weight ranges and viscosity ranges of each of those coatings? So the way you use the chart, if you have a coating, you find it. As you progress to the right, you look at a dot. Any one of those that are dotted, those coaters will work. If you have a coating, you say, what else can I do with this machine? You follow it down to the dots, then you can start looking at those type of products. So based on all that information we gave you and how to select it, this is like a cheat sheet that helps you select the right coating equipment for what your products are going to be. Okay. And then I think the next one's the last slide. Basically, I do work with Davis Standard in what we're offering to the industry based on these knowledges as proven equipment technology to market leaders and the fastest payback due to your increased productivities. We offer the experience. We have product managers. Our engineers are process trained. Our whole group family has been there many years that we know the products, we know the equipment. We have the technology to make all these products. We do solution coating and extrusion coating, so we can handle webs from the thinnest to the thickest, from plastics up to metals. We offer the total solution, which means not only will we engineer, design your machine for you, we will install it, we will start it up, we will train you, and we will maintain it over the years with our field service technology. For any maintenance needs, you can give us a call. Tailored design, we don't offer just everyday cookie cutter equipment. We are known in the industry that when you come to us, we will tailor this machine to give you the best product and for what your needs would be. And global support. We are a worldwide corporation. We have manufacturing throughout the world. We have our service people stationed throughout the world, and we sell to the whole world economy. We're not just a U.S.-based company. Okay, I believe that was the last slide for me. Thank you, guys.
All right, thanks, Lee. Tom, we'll now turn it over to you. Here are some of the topics that Tom will be covering in his Corona treating presentation.
Good morning, everybody. Thanks for joining us, Lee. Great job. Very informative. Tremendous presentation there. So, folks, on the Corona treating side, you'll see some very equal comparisons between defining the application, right? Some of you have talked to me before in the past, and you know that a lot of things Lee brought up in his presentation in terms of the basics of type of materials and web width and line speeds and so on, are the same types of things that we need to know when we're sizing this Corona treater. So in my section of the presentation, we're going to look at, number one, why do we have to treat the film anyway? And then the various types of Corona treaters, why you might want to use them, and then how to use them. How much power do we apply? How do these materials respond, either the same or differently? And then we'll get you guys involved. We'll have you send in some questions, and Lee and I can help you answer those. So next up, Mark. So the number one reason why we're treating these films anyway is you guys have lazy film. The films you have are all low energy. So when you buy a polypropylene or a polyester or a polyethylene film, and you're trying to convert it, and like in Lee's case, we're trying to get a silicone coating to wet that surface. In and of itself, that pre-treated material, as Lee identified in an earlier slide, relative to these starting dye levels, are just not adequate to allow that silicone coating, for example, to wet the surface. Now, why is that? Well, just a couple of reasons. Number one is it's simply a low energy surface to start with, meaning there's no polarity on that surface. It's just a very neutral surface. But then we have other problems, right? We have surface contamination that might be as a result of migrating additives, slip additives, anti-blocks, possibly colors, whatever it is. Some things maybe post-consumer, maybe it's a post-consumer product. There's 30% recycled material in there, and within the scope of that, there was some additives within those categories that now are sitting on the surface, which limits the surface's ability to bond and limit the surface's ability to wet the liquid. So the surface treater, corona treaters or flame treaters, they're there to correct for all these issues. So this is kind of what this slide is showing, right? We're showing a corona treater station and your web with all this baggage, right? We've got additives, we got post-consumer, we got age. The film you're running might have been sitting in a warehouse for any number of months or maybe even a year before it's being converted. So all that baggage that's on that film, we've got to manage that. Somehow that's got to be addressed before it gets into the coating head. Go ahead, Mark. So really what happens here is we have all these low molecular weight materials on the side that are on the surface of the material, and the corona treater takes that material, we oxidize that, we put oxygen into the surface, we go ahead and form these positive and negative sites by adding and deleting electrons in the corona field. And that cleans the surface, of course, get rid of some of those migratory agents that are on there. And when we do all that, we end up now with a surface that goes from a non-polar surface to a polar surface, one that has a surface that was kind of, dirty and not suitable for silicone coating in this case, but now is. And the corona treater is doing its job. It's cleaning and functionalizing that surface so that the coating process does what it's supposed to do. So in a building block method, so here's what a corona treater is. Number one, corona treaters by themselves are pretty simple devices in that corona is nothing more than ionized air. And I'm going to repeat that for you because sometimes this is a concept that gets people a little bit confused. Corona treaters ionize the room air. So you have the air within the room and the corona treater, which is comprised of a power supply, a high voltage transformer, and of course the corona station itself, which is the electrode in the treater roll. When you combine all those things together, the outgoing power that we apply to that electrode ionizes the air that web is traveling in, and we then can functionalize that low energy material that we were just referring to. And what that does, the end result of that is an increase in dye level. So for example, maybe in a propylene material, a pre-treated polypropylene, you might get that material coming from the extruder at maybe 36 dynes, let's say. And then the corona treater can actually, after that 36 dyne material passes through the corona treater, it can actually increase the surface energy to maybe 40 or 42 dynes, depending on various conditions. But that's really what the corona treater is doing, is ionizing air. That ionized air then creates a functional surface on what otherwise is a non-functional film. Next one, Mark. So how do we figure this out, right? How do you know whether the treater is going to be a 5 kilowatt treater or it's going to be, a 50 kilowatt treater? Well, generally speaking, it's kind of the same as trying to help Lee determine what you need for a coating line, right? He needs to know, are you going to coat one side or two sided? We need to know whether you're going to treat one side or two sided. He needs to know how fast you want to convert this product that you're making. We need to know the same. We need to know how fast the treater has got to accept the film that it's going through it for treatment. We need to know what the goal of it is. Are we treating this simply as a result of, just trying to get some material off so the surface energy comes up for a solvent coating, or are we doing it for a water-based coating? Are we doing it for an energy-cured coating, like a UV coating? So these are all the questions that you hear from us when you contact us for a quote. That's why we're asking those questions. We need to get an understanding and sort of define the application a bit so that we know that the treater is going to be a 5 kilowatt treater or it's going to be a 50 kilowatt treater. So, as a lot of you know, there are a lot of different versions of treaters out there. it seems like everything else, right? We used to just have two choices when you ordered a coffee. Did you want it with cream and sugar, or did you want it black, right? Well, today, like everything else, Corona treaters have grown a bit in category. So there are different types of Corona treaters that are used for different types of applications. I won't get into every little nuance here because we're sort of focusing on the systems that are typically used in our example here in a silicone coating application. So I'll sort of focus there. So in that application, and many similar like that, these universal high definition treaters tend to be the ones that people choose. And so, you know, what are they? What makes something a universal high definition treater? Well, there's two main things. Number one, the electrode is actually ceramic. So the electrodes within the electrode assembly are actually a ceramic insulated electrode. And they're designed to be used in various applications. They can treat, you know, standard web, paper, poly, laminates, you know, what have you. But they can also be used to treat conductive substrates. So if you had if you're running a product that in one case is, say, a metallized polyester on one side, and then you're going to marry that, or you're going to coat that surface, the Corona treater, this universal high definition treater, can certainly do that. So it has a lot of capability and a lot of flexibility, okay? The second part of this is the ground roll. So the component in the treater station that's actually there to accept the Corona and then also to support the web as it's running through the treater is coated with a high performance ceramic, blended ceramic formulation. So for some of you who have treaters, when I talk about a ceramic roll, many of you might be thinking of the ceramic coating that you would see on a metal electrode treater. In a general way, they're similar. I mean, they're both ceramics. They're both manufactured in a similar fashion. But in the case of a universal system, that ceramic is applied at a different thickness than a metal electrode ceramic. And it also is comprised of a different powder. So they start with a different building block of material. They apply it in a similar fashion, but the end result then is a different type of ceramic than you might expect on a metal electrode system. And the reason it's so great and the reason it works so well is that it has, while it's conductive, you know, it has to be conductive or we couldn't treat a conductive web. But the other benefits include the fact that it has some dielectric strength. So it helps the web stay flat on the treater roll. So what that means is if the web doesn't pucker or wrinkle under the Corona, you have less chance of getting any sort of reverse treatment or backside treatment, and the wrinkling and puckering issues can be mitigated. Additionally, if you have a substrate, say a very, very thin gauge, like a 48 gauge polyester or something of that nature, or let's say you have a coated paper that has a very, very light poly coating on it. And I'm thinking, in my mind, you know, to give you a picture, think of a coffee cup. You know, you go to Starbucks and you get a coffee. That sort of product, if you're not cautious with how you design the treater, and in this case the backing roll of the treater, you could inadvertently cause pinholing on that product. And of course, if it's going to be used as a liquid product to hold coffee or something else, you certainly wouldn't want to inadvertently put a pinhole in the product. So again, you know, the universal treater here sort of has a nice umbrella sort of effect and does a great job for a lot of applications in the coating space. And it does produce a very high density, high definition, very uniform, less filamentary, you know, less lightning bolt kind of Corona for these materials. Next slide, Mark. So how do you measure the effectiveness of treatment? You know, you could do a webinar easily just on this topic alone. So what I did on this slide is I sort of ran everything together and gave you the sort of the high-level approaches of doing this. The number one message I want to leave with you guys in this section, the thing I don't want you to forget, I want everybody to remember this. Dye testing, which we all use, and most of us are quite familiar with it, is sort of the industry's standard method for determining the effectiveness of the treater. And so I'm going to go down this road a little bit with you and try to put a little context in this for you. So to measure the surface of a surface area of a film with a dime test, we can do it with pens, we can do it with sterile cotton tip swabs, and we can use a drawdown or a Meyer rod method. In our opinion, dime pens are best used for initial testing. So let's go all the way back. Think with me for a minute. Go all the way back to the early slide in Lee's presentation where he had that list of all those materials and where they start and some generalized die numbers in there for the coating. So picture yourself here, folks. You're an operator on a coating line. You're on the main on line. Your inventory group just brought a bunch of rolls over to you to load up on the machine. These happen to be rolls of film. And we'll just say for the sake of this conversation, they're rolls of polypropylene film. Now you look at that as the operator and you know, based on the data you have, that one side of that film is supposed to be pre-treated, and that's the side that you want to load properly so that it goes to the treater, again, to bump treat it, and then coat and dry and so on, right? How do you know that? How does that operator know they can't see it? They all look the same. So for him to determine this, the best method, quick and easy, take a dime pen. So if the specification for that material that's coming to you, and these are just general numbers, but let's say it's supposed to get to the, get to your line at 36 or so dimes. The operator takes a 36 dime pen, does a real quick test over the roll, confirms which side is pre-treated, puts it up on line, we're off and ready to go. Simple, easy, ready to go. If you then want to look at the corona treater after you bump treat this material and say, well, what did the treater do? How do I know at this particular power and particular speed that I got an increase in 4 dimes? Let's say my target's 40 dimes. How do I know that? Well, at that stage, then you have a couple of choices. Actually, you have more than a couple. You can do the ASTM dime test method, which uses sterile cotton swabs, and I put the ASTM test method number on the screen for you so you can look it up through ASTM. Very effective. Has a little bit of drawbacks, kind of can be a little bit messy. As with a dime test in general, there's some interpretation there. So you want to make sure that you people that are charged with doing this for your organization are fully trained and understand the test method. But it's a documented method. You can teach and train people and have the documentation in front of them so they repeat it. A little bit of a corollary test to that is the tapping T552 method, which is using a drawdown rod. Now, in our slide here, on the right of the slide and the lower picture there, you'll see the drawdown method. I am a big fan of this method, and I'll tell you the reason why. In that slide, you'll see a piece of film on a clipboard, and just for the sake of conversation, let's say that the far left drawdown is 38 dimes, the middle one is 40 dimes, and the far right one is 42 dimes. You take that number 4 or number 6 Meyer rod, you draw them all down at the same time. So you have an instant comparison between each drawdown right then and there. You don't have to go out and get another pen and remember what the last one looked like or anything like that. The Meyer rod does a great job of smoothing and drawing down an equal amount of coating of dime solution. And some of you may have never thought of this, but for those of you who have tried the cotton swab method, that ASTM method, you have practical experience and know that if you load up that cotton tip swab with too much solution, you can kind of get the dime number to be whatever you want it to be. Because it's got so much solution and the solution solvent based. So you can, if you're not mindful of what you're doing, you can get that to kind of give you the wrong answer. On the other hand, if you're using a drawdown rod or a Meyer rod method, it meters that dime solution uniformly all at the same time, and you can see instantaneously where it's receding, where that dime solution is breaking up, and it's usually on the edges of the drawdown, which is really important because as you go forward on this test method, you're looking really for consistency. How consistent are your results day after day after day when you do these tests? And in my opinion, in my years of experience, I recommend highly using a drawdown rod test method, for your dyne testing. Now, it does have disadvantages. You're probably not going to do that test on the side of the line. It's going to go to a QC department or somebody's office or something to do it because it's just not convenient to do it, right by the machine. So that's a bit of a downside. But I think that downside, while there, I think the upside of the consistency and the ease with which you can read it and have these consistent results time after time, I think are pretty huge. Now, the next way we can do this to measure the effectiveness of treatment is a contact angle, and there's many different versions of those out there. They've been around for a long time. And basically what you're doing is you're taking a measured drop of a liquid, usually deionized water or some such liquid, and you apply it precisely to a very small sample of the treated sheet. And the droplet, is applied, and you're looking at the contact angle of that droplet on that surface. So really, they're measuring how much that droplet spread, and then measuring the angle of that. The benefit of that is it is very measurable. It's very precise, right? It's kind of right in front of you. There's really not a lot of interpretation there. So you get a very direct answer. You know that the contact angle went from 80 down to 20. So you have these values. Unfortunately, that doesn't, in our business, that doesn't necessarily tell you anything relative to how the coating is going to perform. Because there is no particular connection between a dyne number and a contact angle number, okay? So it's another data point, and it certainly is useful to collect. There's nothing wrong with, having another point of information there, but they don't really necessarily directly connect with each other. And so that's a little bit of a downside to that. Then the second thing that's a little bit of a downside is you're only dealing with this very, very tiny point area on the web. In Lee's example, a coating line might be 6 feet wide or 7 feet wide, right? So we got a 7-foot wide coater, we got a 7-foot wide web, and we're going to determine the contact angle of a dot somewhere on that web. Now we're going to make the assumption that it's the same all 72 inches. I mean, it'd be a hard thing to do. It doesn't mean that the test method doesn't have its value. In certain cases, or as another data point, it has value. But again, it's all context, right? How are we using it? What is the context with which we're using it? And then finally, and maybe even more important than any of the other ones above here, what happened? We unwound it, we treated it, we coated it, we dried it, right? Now what are we going to do with it? What's your peel adhesion value of that coated and cured product? So I would challenge you guys out there today to consider this. I would ask you guys to record the watt density with which the treater treated the substrate. Record the initial dynes, the treated dynes. Look at your wetting. If that passed, great. You're good. And then the final data point there is your peel adhesion number. Is it within your target? And if those numbers all line up time after time, you're going to be pretty sure that your customer is going to be happy with that end product. And if for some reason somewhere down the line he calls you and he's not happy with it, you have this very complete picture of application data then, where you can go back and look at it and say, hey, where were we here? What happened? What data point was off? Did we start off with a roll of film that wasn't 36 dynes? Maybe it was only 32, and we tried running it. Did our drawdown rod dyne level drawdown cap, did it look poor? So you have all this data that you can collect now, that's meaningful data, that you can then go back and use to help your customer in the event it's required. Next slide. So here's my controversial slide of the day. So dyne levels do not guarantee adhesion. I just came back from a few days of visiting with customers, and I think I must have mentioned this at least in 3 different meetings this week. It's a little counterintuitive in our industry, and the reason it's counterintuitive is because Just by happenstance, we take a substrate that's 36 dynes, we treat it to 40 dynes, we put some silicone on it, we do a peel adhesion test, and hey, look at it, it's great, it works. And everybody thinks, hey, 40 dynes equals this great adhesion. Well, not necessarily, right? So dye numbers are measurements of wetting. Adhesion is not that, okay? It is fortuitous, and it's quite helpful to us that they tend to follow along in the step-by-step manner. But the truth of the matter is, and many of you out there that are listening to me now, you know this on your own. There's many of you who have had the same experience wherein you treated the substrate, you applied the ink or coating or adhesive, and you didn't get the result you want. Yet at the same time, you may have recorded the dye number that in the past looked good. So at that standard, you'd think, I don't know what's going on here. Something's wrong. Why is it that I got this dye number and now I don't get the result I want? Next slide. So what do you look at, right? When that happens, what are you looking at? Well, you're looking at what kind of output power did you have? Was your watt density where you needed it to be? How am I controlling this treater? So these two methods are the most common methods. You can just control the treater through simply walking up to the controller and raising or lowering the kilowatt output. In that example, and many of you do this, you know the old saying, raw power, right? If 1 kilowatt is good, 10 kilowatts has got to be better. Well, sometimes, I mean, it's not like that ever happens, but that's kind of the rare case. Really what you want to do is you want to sort of suit the output power to the material. So let me give you an extreme example. Let's just say we're running polyester film. We got it on the silicone coater. It's very thin gauge film. And maybe we're in a mode where we're running slower. Maybe the job requires that for whatever reason. Line speed is a bit slower than what we would normally do. But we decide that even at the slower line speed, we're going to give, whatever that treater output is, we're going to give it 100% of that treater output. Well, what happens there is you will find many times some odd things that can go on with the web. The web gets into the treater, it's running at a lower speed, gets a lot of dwell time, a lot of power, and now the web starts doing odd things. You know, it can pucker, it can wrinkle, it can get a big static buildup, things of this nature. And then when the web exits the treater, then more problems happen. The coating doesn't look right, it doesn't wet properly, maybe it's got sort of an orangey peel look or something. You know, something in that process is not working. But you're moving, right? The web is moving. It's all happening at the same time. And so by the time you might recognize this, maybe it comes out of the dryer that way. Well, now you've run how many feet of material that actually goes where? What can you do with it? It's going in a dumpster. And so running just with kilowatts and, you know, it's a touchy-feely kind of thing, yeah, I mean, you can do it. It's good. But a better way of doing it is controlling your treater to a watt density setup. And the watt density is something we're going to go into right now. So really what we're looking at is we take into account the width of the web, width of the electrode, if it's a fixed width electrode, and we're looking at the width of the electrode, the line speed, the number of sides we're treating, and we calculate all this out, and we come up with the amount of energy based on the line speed and the web width. So how much power over how many feet squared of material through the treater per minute. So let me give an example here online. Formulas are hard to do on a webinar. So if any of you have questions on this after the webinar, you can reach back to me. I'll be happy to go over with you. But so let's just say, for example, we have a 5-foot web. We're running 500 feet a minute, and we're only treating one side. So what that tells me is I'm running 2,500 square feet of material through the treater per minute. I want to apply 5 kilowatts to it. So I take 5 kilowatts or 5,000 watts, I divide that 2,500 square feet into 5,000, and I end up with a watt density of 2, which is what you see in front of you on the slide. So you might be asking, well, you know, that sounds great, Tom, but so what? You know, well, this is how all corona treaters are sized. I don't care if the corona treater is a ceramic electrode corona treater. I don't care if it's a bare-roll corona treater or metal electrode corona treater, or for that matter, an atmospheric plasma treater. These are all sized in the same fashion. They're done the same way. in a general rule of thumb, most corona treaters today that are supplied are sized somewhere between 2 and 3 watts per square foot per minute. Again, general point, but if you're running pre-treated film and you're just bump treating this material prior to silicone coating, as our example illustrates, likely somewhere in that 2 to 3 watt density will give you a great result. So if you can get yourself tuned into this sizing method, this measurement method, and you use this on a regular basis for your key products, and you tie it in with peel adhesion number, die number, maybe a contact angle number, if you tie these data points together in one page, you end up with really some very powerful data that can help you troubleshoot in the event you have a problem. Next slide. So again, here we go, right? Generally speaking, higher watt densities produce higher die numbers. We've all seen this, right? We have practical experience here that tells us. You know, maybe the other bit of data on this slide underneath it should say, generally speaking, higher watt density produces higher die levels, and underneath higher die levels you say, duh, right? That's what everybody's thinking. But really, that's not always the case, right? That's not always the case. And again, your own experience shows this. So let's go on to the next slide and we'll dig into this just a little bit. So you can't use a watt density to predict your die levels. Many of you want to have this sort of closed loop system that says, when the corona treater's on and I run at a watt density of 2, I'm gonna get 42 dynes. And believe me, if I could do that for you, I would be glad to do it. It's not a question of equipment or technology that doesn't make that happen. It's really the overall reason that doesn't happen is the material. Over time, somehow the material in this equation, the polyester, polypropylene, polyethylene, styrene, you know, whatever the material is, has kind of leaves our thoughts. You know, we kind of set that aside. I guess it's like wallpaper, right? The material's got to be there. You're making, you know, in our example here, we're making silicone-coated product, right? So the material's got to be there. We've got to coat something. And so we kind of set that aside. And sometimes we set aside the fact that the material changes. You know, we might be coating one type of film one day, and the next day we have a different job. We're still coating it, but we're coating a different type of material, and we assume that they're all the same. And so therefore, if I ran 2 watt density yesterday, I should be able to run 2 watt density today, and I can predict then that the dyne level is going to be equal. And that's not really the case. Next slide. So what is your expectation? When you turn your corona treater on, do you just expect it magically to sort of give you this die number? Because if that's your expectation, there are going to be times you're not going to be happy. Do you expect to see that same result every time you run the film through it? Again, if you do, your expectation may not be met. So why is that? There are all kinds of reasons, but really the main reason is the film structure and what's going on the surface. Polypropylenes don't treat the same as polyethylenes, that don't treat the same as styrenics, that don't treat the same as polyesters or nylon. And again, we know this. So let me give you a really drastic example there, okay? So on one end of the scale, I have a polyester film. And again, if I go all the way back to the beginning of the presentation and we look at Lee's slide there, that polyester film came to us at probably 38 or 49 without any further treatment. On the other end of the scale, if I take a polypropylene of the same gauge, same width, right, and from 10 feet they look the same, that polypropylene isn't anywhere near 49. So just on that alone, just by that reality alone, is it right to expect that at the same watt density, you're going to end up at the same point? That's just not going to happen, okay? And so the dyne level that you start with matters, and then the substrate matters. The time the substrate's been around, how old is it? What additives are in there? Is there any other surface contaminations in there? So many times on converting equipment particularly, you always hear, and you heard it from Lee, to be successful in converting application, printing, coding, what have you, you need to be using pre-treated film. And it's got to come from a vendor that's reliable, that can provide you film that's treated at a reasonable level, uniformly, all the time. And then your responsibility on this is to watch your inventory. Manage the inventory, store it properly, don't leave it sitting out in the parking lot, don't leave it sit there for 6 months. Watch how you rotate your inventory, how the rolls come in and out, and make sure you use them in a manner which is suitable for silicone coating and for your end product. So if you do that and you bump treat that before you coat it, and we had his line schematic there where he showed a couple treaters that are in there, that's really what he's doing. He's unwinding those films and he's bump treating them prior to the coating process. Next slide. So here's a great example of what I was referring to. So we have 3 different films. We have a pre-treated polypropylene, we have a polyester, and we have a polystyrene, right? And we treated them all exactly the same. So it's the exact same treater, and at the same power. We treated them all at a 1.1 watt density. So what results did we get? Well, on the pre-treated polypropylene, we didn't get much, right? We got maybe 34 dynes or something like that. On the polyester, look at that. At a watt density of 1.1, that's a big winner by the dyne category. We got 45 dynes on the polyester. And the overall winner altogether in the dyne race here is polystyrene, where we went from, the low 30s up to 60 dynes. So if all we were focused on was just this dyne number, like we're racing towards dynes, then clearly the winner here is polystyrene. But isn't it interesting? Don't you find it interesting that we got this great number, but the treater didn't change? The treater is the exact same device running at the exact same power. Let me ask you guys out there, what in that example changed? And of course, the answer to that is the film changed. So different films treat differently. Next slide. So again, really a good example here where we had BOPP versus polypropylene, and you apply different watt densities and you don't get the same dyne level results, right? It's really the same category. Depending on the film structure, additive loading, age, and so forth, some films respond better to more aggressive amounts of corona treatment. Like in this particular case, watt density of 2.2 gave us one result with one film, gave us a different result with another film. And as I go up in power here, at a watt density of 4.5 almost, I still ended up getting some benefit. But on the other hand, on the other film, I got nothing. It sort of plateaued out. So the film, folks, the film makes a huge difference in terms of the ability for you to convert it accurately and effectively. Next slide. So again, looking here at a low-density polyethylene and the dyne level change there relative to the increase in watt density. Now, the purpose of this slide is interesting in that we have this conversation all the time, and Lee might probably chuckle a little bit at this. Sometimes when we go through this analysis process and we're collecting data from you on application, we will get the comment will come back to us where somebody will say, well, I need 56 dynes on this randomized list of materials, or I need 50 dynes or something like that. And where that comes from, I'm not exactly sure. I'm not aware, and I'm not, which doesn't mean there isn't any, but I'm not aware, generally speaking, of any solutionized coatings or inks that are water or solvent that are formulated in a manner that requires the substrate to be anywhere near that dyne number. Most of the time, those dyne numbers are asked for because people are making an assumption that I'm going to store this stuff, and then in 6 months it's going to be high enough yet that I'm going to be able to then still coat it or print it or something. There's a lot of trouble with that thinking, least of which is the fact that these things don't all decay at the same rate. Sometimes they drop very fast, sometimes they drop very slow. it's like playing Russian roulette with that. You just don't know what's going to happen over time, okay? But even worse than that is it costs you guys a lot of money. And so we'll go back to our watt density calculation, right? We had a watt density of 2 in that slide. That gave us 5 kilowatts, okay? Let's just say that 5 kilowatts gave us 40 dynes. So now, if I wanted to get to 52 dynes, I'd have to more than triple the size of the treater in order to get to 52. If I wanted 56, I'd have to make the treater 5 times the size of that 5 kilowatts. And let me tell you folks, there's a big difference in both equipment size and price between a 5 kilowatt treater and a 25 kilowatt treater. So watch what you ask for. Be mindful of what this dyne, sort of this race for dynes is actually doing. And frankly, it's not helping you. It's really kind of clouding the issue, and it doesn't really help you get to the right, get to the right equipment really. And that's where a company like David Standard and Lee and his team and Enercon and our team and our engineering group, we can really help you sort through all that. I mean, that's really why we're here today, to make sure you understand these subtleties so that you don't make that kind of mistake. Next slide. So when you don't get a result that you expected, and that happens, right? We go back to our old slide, and we saw that slide where we applied a certain watt density, and we may have expected a certain dyne number, and we didn't get it, right? How do you fix that? Or how do you troubleshoot that? Now, you can certainly call Lee and ask him. You can call Enercon and you can ask me. But really, on your own, if you feel it's a treater problem, there's a very simple way to deal with this. And we'll go through a little bit of this today, right now. So has your setup changed? Did somebody go over there at the treater, you were running in watt density mode, somebody switched it to manual mode, but didn't tell anybody, and now you're thinking you're in one mode, but you're not, and so therefore the treatment you thought you got, you didn't. And is that affecting, the situation? Is your line speed changed? Has somebody in the mix got a job confused? They're running it either faster or slower than what they were supposed to, and therefore the outcome of the treater is not what you want. Has the film changed? This is really a critical step here. Many of you will have multiple vendors. So let's say, again, on our example here, silicone coater, we've got a polypropylene web. We've got 3 suppliers, and they're all running, they're supposed to provide the same polypropylene, same width, same gauge, same tensile strength, same everything, right? It looks the same. And again, from 10 feet, these all look alike. You may be expecting, or your expectation might be, well, they're all the same, so they should all treat the same. Well, you can run through a period of time when that's the case, but I can guarantee you at some point, one of those vendors, one of those rolls is going to be out of sorts, and it's not going to treat the same, and therefore it's not going to convert the same, and you're going to have to figure that out, because you can't see it. You can't look at the roll and say, hey, something's a little wrong with that roll. It's just the nature of our business. So that's the importance of sort of doing that preliminary test with that roll before you get it up. If it's supposed to be 36, but in this instance, it's supposed to be 36 times, but the operator only measured it at 34 or 32, before you apply money to the web, before you turn that silicone coater on, you may want to take that roll off there and get a roll that's at the right condition. Because there's a good chance that roll you put on there now is not going to run right. So it's really asking that question, right? What changed? What happened between yesterday and today? Next slide.
All right, thanks, Tom. Thanks, Lee. Very insightful presentations on the topic. We're going to move into our question-answer session next. If you guys want to reach out to Tom and Lee separately, you certainly can do so by contacting them at those email addresses and phone numbers. The first question that we have is, what coating method is preferred for porous substrate, for example, non-wovens? Hang on one second, let me finish the second part of this question. Porosity of substrate would be higher than 60%.
Well, typically on that, you would do a KISS-style coating, where you would be applying the coating with some sort of a roll, let's say a gravure roll, and you would drag it over the top of the roll, contacting it about 1.5 inches, and you would have an idler on either side. Or if you wanted to be more precise, you would still do a KISS method, but put a slot die instead of a roll there. And with some special lip designs, you would bring the web in contact with the die, but not have anything on the back side of it. You'd be kissing it, and you can control the amount of penetration into the porous substrate based on the back pressure, based on the flow rate of the die and the lip openings.
Thanks, Lee. Here's another question. It was mentioned that flame treating is sometimes used on a coating line. Tom, can you talk about when a flame treater might be used versus a corona treater?
Yeah, flame treaters are great devices. They generate a lot of energy, a lot of power. And so when you're running a substrate on a very fast line, if you're running a couple thousand feet a minute or greater, 3,000 feet a minute, let's say, and let's say the substrate might be more of a porous substrate, like a craft paper or a board or something of that nature, maybe prior to extrusion coating. Flame treaters are great devices for those sorts of products at very fast speeds. They are great devices that deliver a lot of energy in a short period of time. And when the substrate's a little thicker, or maybe the gauge is not quite, great, it's not a totally flat substrate, flame treaters can be very effective there. They don't care, they don't care. They don't have a tight gap that you got to run through, and so they can be quite effective there.
Thanks, Tom. Lee, what would be the relationship between viscosity and foaming in the pan for roll coatings?
Well, typically, the higher the viscosity, the less the coatings are going to churn and mix. So you would expect to have less foam with a higher viscosity coating. The lower it is, the more I can move it, blend it, and mix it together, and that type of action creates foam.
All right. Tom, here's a question. Can you couple line speed with watt density for a joule density metric?
Well, so it's either joules. So you either size the treater for, and I don't have the right description in front of me, but it's joules per square centimeter, I think. In any event, so you can either size the treater in two ways. The end result is the same, but depending on your metrics, if you're using watts per square foot per minute, or you're using watts per meter squared per minute, or using joules, you just really what you have to do is just let the supplier know how you're measuring your output of your treater. Are you doing it in joules? Are you looking at a watt density in meters? Or are you looking at it in square feet? Once we understand sort of what your metric is, then we can take that metric and we can apply it to our sizing tool.
Okay. Here's a question. There's a converter there who uses a nip with their corona treater, but at certain times they may see some backside treatment in solventless lamination. What could be the cause?
Well, the simple answer is backside treatment is the cause of backside treatment is always the same, and that is you get air behind the web. So if you start at that point and you start troubleshooting that, the main question then is what changed? Why is it in some cases that air is getting there where in other cases it's not? Could be, it could be the film gauge. It could be a film gauge issue. If it's an equipment issue, meaning like the nip roll cover needs replacement, or you have a treater roll that's a little out of round, or something of that nature, that would be repetitive, right? You'd see that every time you ran the laminator. You'd note that. So it may be related to the conditions at the time when you're converting. Another thing I checked there is when that occurrence happens, are you driving the treater rolls? Are they turning at line speed? That just occurred to me. In that example, if when that occurs, you're running at a faster speed than other occurrences, you could get some laminar air that's causing that web to float. And if your web tension isn't quite great through the treater, and you're not using the nip roll at that stage, it is conceivable you get a bit of an air buildup back there. And if you get air behind the web and it goes under the electrode, as we said earlier, corona is just ionized air. And so there's a chance that you're going to get some corona back there, and that could give you some backside treatment.
Lee, can you talk about some of the considerations and trade-offs between configuring a line for single pass versus multi-pass?
All right, when you look at running a web with a coating through a machine line, you have to look at what's happening during the process. We used tapes earlier today. So when you're doing a silicone coating, depending on the temperatures, you could actually get some degassing, some particles, some dusting of the silicones coming off in the dryers. So now that gets stuck inside the dryer format, and we got air blowing around in there. Now I bring an adhesive coated substrate through that same dryer, and those particles could dislodge, hit the web, and silicone at that point will repel the adhesive and give you voids in the coating. So one of the biggest downfalls with running multi-pass is contaminations from previous runs of different type of coatings and substrates.
Got it. Very good. Tom, how deep in the substrate does the corona treatment process go?
Well, it's a great question. There's a reason that it's generally called surface treatment, because that's really what it is. The surface of the substrate, the corona treatment only goes a few angstroms deep into the surface of the substrate. And for those of you who are used to using corona treaters, you've likely seen this yourself. You're doing a dye test, and you take a piece of treated film and you handle it, maybe you have your hands on it, you're just handling it to put it down so that you can do your dye test. And in the course of doing that, you get an answer you like, dye number you like, but as you're drawing that pen across it, you might find that the pen gets across where your finger was, where your thumb might have been. And you see that in that area, it's not the dye level that you needed. And really what's happening there, and it just shows you an example of the fragility of surface treatment in some cases, to where, the oil from your skin there is affecting the surface. And so when the dye pen went over that, you can see that right where your oil from your hand was, it's not as good. This is principally the reason that, like in Lee's slide there, where he showed the machine line configuration, most of the time, 99% of the time, you see the corona treaters right before the process they're intended. So the web's coming off the end line, it's going through the treater, and it's going right into the coating head. And there's a reason for that. We want that treated surface to go right from the source, right into the coating. We don't want to have any areas where the web could get recontaminated with anything, whatever it happens to be.
Lee, we have a question on how does drying and curing dwell time compare between UV cured coatings and water-based coatings?
A UV cured coating is determined by the amount of initiator that's added to the formulations that you put into it. So let's say if I were to take a water-based silicone versus a UV 100% solid silicone, they're not even comparable, in this realm. A water-based, you have to get rid of the solution water and then hit it with a temperature to cure it, and it takes so much time at a temperature. Whereas a UV, it takes a certain power from that wavelength of light to initiate that chemical. And the more power you have in the light, or the more initiator, cuts down the amount of time. Now, typically, we're in a UV system. That's on silicone coatings with 2 banks, which is 2 rows of light. You're hitting it twice. You can do typically 1,000 to 1,500 feet a minute. When you go above those speeds, so let's say at 1,500 to 2,000, you might add a 3rd lamp. Whereas when you change speeds with a solution coating in dryer dwell, now we're looking at, all right, I need energy for so many seconds. So it's going to be a predetermined amount of time. It's just a dryer length change per second. So they're not really a comparable number, but it's a footage. Like a UV system will take, let's say, 4 foot, where a dryer can take 60 to 150 feet.
Thanks, Lee. We've got one final question. Tom, this one's for you. Is corona treatment required for polymer non-woven substrates?
Well, it's a good question. Again, kind of leaning on Lee's earlier part of his presentation, it really depends on what we're putting on there. So what's the ongoing chemistry that's on that nonwoven? Corona treaters, atmospheric plasma treaters can be used and are used, frankly, for polymer nonwoven. And they're used really for the same reason that you use them on a film. We're trying to clean off anything on that surface that inhibits the ability for the coating or ink to wet. And so is it needed all the time? Really hard to answer that in a general way. But generally speaking, I guess if it's a water coating or energy cured coating, I would say yes, you'd want to surface treat that before you coated it.
All right, thanks, Tom, and thanks, Lee. Also like to thank our audience today. You will receive a copy of this or access to this presentation via an email, hopefully within 24 hours or so. If you have any questions, please follow up with Lee and Tom. If you have ideas for future webinars for us, please let us know. We appreciate your attendance today, and this will conclude today's webinar.